So we did the means of independent samples and then dependent samples. So now we're going to be testing the difference between proportions, two different proportions. And so to do that, we're going to be using a z-test. I already included this on the flow chart that I made because I posted the chart like before the exam, and I thought I'm not going to leave out section 9.4. So this situation is already included on your flow chart, even though we hadn't learned it yet. So that's already on there in case you want it. Okay, so there are a few different types of hypotheses when we're doing the difference between proportions, but they don't look too different from things that we've done with means. So remember that our null hypothesis is always going to have an equal sign. So if we're testing the difference between two proportions, I'm going to call them P1 and P2. So my null hypothesis is going to be that P1 is actually equal to P2. And then an alternative hypothesis could be that P1 is not equal to P2. Okay, well, my null stays the same for all of them, so this is still P1 equals P2. And then another alternative hypothesis that we could have is that P1 is greater than P2. Okay, so our null hypothesis C is the same, that P1 is equal to P2. And then our last option for an alternative hypothesis is that P1 is less than P2. You're all good, Cameron. Let me just mark you as present before I forget and I can absent. Okay, we're all good now. All right, so these are our three types of hypotheses when we're testing the difference between two proportions. Nothing too new. We've seen these three types before. Now we're just dealing with P1 and P2 instead of like mu1 and mu2. So obviously we have a formula. So this is our formula for the z-test. So let me go ahead and write it down. So it is going to be z is equal to, and this one looks a little complicated. It's P1 hat minus P2 hat minus P1 minus P2 all over P bar Q bar 1 over N1 plus 1 over N2. I would say this is probably one of the more complicated ones that we've seen. And like it says down here, for the test statistic, we need P1 hat and P2 hat. Oh, actually, this one doesn't say that. Which are the sample proportions for each sample. So we'll do an example problem and you'll see that we'll have sample proportions for each of the two, each of the two samples. Okay, so let's talk about what really is P1 hat and P2 hat. So it is the sample proportion, but let's write it out as P1 hat is equal to X1 over N1, and P2 hat is equal to X2 over N2. And all that means is that if you're given like an example where it says, oh, I don't know, like 15 or I don't know, 80 people were surveyed and 15 of them have received a speeding ticket, the proportion would be 15 over 80. So that's what that means when it says X1 over N1 and X2 over N2. It's just that you have the number of people that something applies to them or is true for them over the sample size of the, well, I guess the sample size. Okay. And then it says when P1 and P2 are unknown, a weighted estimate of P will be computed using the formula P bar equals this whole thing. Oh my gosh, this is gone on this one. Let me write it in. I don't know why it always does this. Okay, P1 and P2 are unknown. Okay, by using the formula P bar is equal to x1 plus x2 over n1 plus n2. And then Q bar is equal to 1 minus P bar. You can see in our formula for the z-test, we have P bar and Q bar, and then down here, that just tells you how you're going to compute that. So P bar is equal to x1 plus x2 over n1 plus n2, and then Q bar is just 1 minus P. Okay. So just a little note that's in the textbook that's also in here. It is required that your samples have to be independent of each other, and that N1 P1 and N1 Q1 must be 5 or greater, and N2 P2 and N2 Q2 must be 5 or greater. I am never going to give you a problem that this doesn't work for. So I'm never going to give you something that like doesn't meet this criteria that you have to somehow know, oh, it doesn't meet this criteria, I can't do this. I'm not going to give you that. This is just like something the textbook says, hey, just so you know, this is required to do this process, but I'm not going to give you anything where you have to check that it meets that criteria or that like it doesn't meet the criteria. All right, and then lastly, it says since we're using a z-test, we're going to be using table E. All right, so that kind of like sets everything up, but now we can go ahead and try applying this on an example.
On that formula, you put Q bar. We're looking. It's a Q bar is supposed to be, or sorry, not Q bar. P or P bar instead of P hat. Is it supposed to be P bar?
Yeah.
Formula?
So this is this one, right?
Yeah.
Yeah, that's supposed to be P bar. Yeah, because in your formula right here, you have a P bar and a Q bar.
Okay. Thank you.
Yep. Okay. All right. So our example here. So I'll go ahead and read it. In a nursing home study, researchers found out that 12 out of 34 randomly selected small nursing homes had a resident vaccination rate of less than 80%, while 17 out of 24 randomly selected large nursing homes had a vaccination rate of less than 80%. At alpha equals 0.05, tests the claim that there is no difference in the proportions of the small and large nursing homes with a resident vaccination rate of less than 80%. Use the traditional, oh, I should say traditional. Use the traditional method of testing. So this tells us that we looked at 34 randomly selected small nursing homes and found that 12 out of them had a vaccination rate of less than 80%. And then we did the same thing with 24 randomly selected large nursing homes and found that 17 of them had a vaccination rate of less than 80%. So those are our two proportions there. And then we have the significance level, and then we're testing the claim that there's no difference in the proportions of these small and large nursing homes with a resident vaccination rate of less than 80%. Okay, so step one is to always write your hypotheses. So our null hypothesis is never too bad because it's always P1 equals P2. I don't care what the claim is, I don't care what's going on. Your null hypothesis always has an equal sign in it. But then the alternative, we kind of have to figure out. And so it says, because we're testing the claim that there is no difference in the proportions, our alternative hypothesis is just going to be that they're, oh, sorry. Oh, I wrote H1 again. Oh my gosh. Hold on. P1 is not equal to P2. Doesn't say anything about it being like less than or greater than in the proportions. It just says something about there being a difference. So our alternative hypothesis is going to be that there is one. They're not the same. It can be one is greater than the other or the one is less than the other, as long as there's some form of a difference. But our claim actually says that there is no difference. So that means that our null hypothesis is going to be the claim here. All right, so we do need to find the critical values from the appropriate table. So in order to do that, we just need to know the significance level. So alpha is 0.05. And then we also need to know that this is a two-tailed test. And that's because we're looking at this normal distribution here. And because we have a two-tailed test and a significance level of 0.05, we know that the area in these tails, we want to equal 0.05. But if we have two tails, that means that in each tail, it should have an area of 0.025. So let me draw that really quick. So right now we're drawing our critical regions here. So this is our critical region, this is our critical region. So we know between the two of them, we want to have an area of 0.05. So that means that in each of them, we need an area of 0.025. So if you remember how to do this, we have to go to our table. And because we're doing a z-test, we need that z-distribution table with z-scores. And we want to find the z-score that's associated with an area of 0.025. I'm not going to go through the process of doing this, but spoiler alert, it is 1.96. So your critical values are positive and negative 1.96. All right, so since we're doing the traditional method of testing, now we just compute the test value and see if it falls in the critical region or not. So let me write down our formula and then we can work on filling in the pieces of the formula. So z is equal to p1 hat minus p2 hat minus p1 minus p2 all over p bar q bar 1 over n1 plus 1 over n2. Well, if you remember when we've been doing the hypothesis testing with two means, this usually showed up in our formula as well. We had this thing that was like, with the means, it was mu1 minus mu2, but in our case, it's p1 minus p2. And if you remember, I said, hey, when our hypothesis has in it like p1 equals p2, this is 0. So same thing applies here. Just like with the means, when I said, oh, if our hypothesis has mu1 equals mu2, then this part is just 0 in the formula. Same thing here, but it's just with proportions. So I'm not going to give you an example that's not 0. So yes, this is the formula for getting the test value, but in all the examples that I give you, P1 minus P2 will be 0. So you don't have to worry about having to fill that part in. You could do some more like complicated examples where they talk about having a specific difference between the proportions. So like not just a difference, but like a specific difference of maybe like 20%. That's the case when there you use an actual value and it's not just 0, but in the examples that I give you, I'm not going to do that. Okay, so now we need to figure out what P1 hat is, P2 hat, P bar, and Q bar. All right, so let's start with P1 hat. So P1 hat is the same as X1 over N1. So if we come up to our word problem, we see that our first proportion is going to be talking about the small nursing homes. And we find out that 12 out of 34 of them have this vaccination rate of less than 80%. So that means that our P1 is 12 out of 34. And I'm going to write this as a decimal just because it's going to make it a little easier. I'm just gonna round, but I think when I did it before, I actually rounded wrong. Oh, Oh, no, I didn't. Hold on. Nope, we're all good. Okay, this should be 0.35. You could leave it as fractions when you go ahead and compute it, but I'm just going to write it as a decimal. And then let's do P2 hat, and this is going to be the proportion from our second sample. So then we talk about these large nursing homes, and we get told that 17 out of 24 of them have this vaccination rate. So our P2 is just 17 out of 24. And that's about 0.71. All right, and so then we have to figure out what P bar is. And P bar is equal to x1 plus x2 over n1 plus n2. So we actually already have all those things because we put that P1 hat was x1 over n1. So we know that x1 is 12 and x2 is 17 and then 34 plus 24. So that gives you 29 over 58, which is just 0.5. Okay. So now we have to find a Q bar, and Q bar is just 1 minus P bar. So it's just 1 minus 0.5, but that's just 0.5 again. Okay, so now we have all these things that we need. So we have P1 hat, P2 hat, P bar, and then Q bar. So now it's just a matter of plugging them in. So we get Z is equal to 0.35 minus 0.71 minus 0 over the square root of, let's see, 0.5 times 0.5 times 1 over, and N1 was 34, plus 1 over 24. Okay, and then to plug this into a calculator, all right, we should get negative 2.70. So that is our test value. Okay, so step 4 is always make your decision to reject or not reject the null. So we're doing that traditional method. So we need to see if our test value falls within the critical region. So what do you guys think? Reject or not reject the null?
Not reject.
Not
Reject.
quite. Yeah, reject the null. And we're rejecting the null because the test value falls within the critical region. I know sometimes it's confusing and it's really easy to mix it up, especially when you have to know the p-value stuff. It's just a lot. So, but in our case, negative 2.70 falls over here. So it does fall within the critical region, which means that we reject it. Thanks for participating, everyone. It's always nice. So we do reject the null in this case. In step 5, we just have to summarize. So it's going to take me a hot minute to write, but there is enough evidence to reject the claim that there is no difference in the proportions of small and large. This is like the longest conclusion I've had to write in this class so far. Small and large nursing homes with vaccination rate of less than 80%. There we go. All right, and we're able to say that because we rejected the null, and the null hypothesis was our claim. So we're able to say that there was enough evidence to reject that claim. All right, any questions on anything I did or wrote, or on just anything I did on this example? Okay, so per usual, I put one more example in here, but it's using the p-value method instead. So this one's about, let's see, it's about criminals and being arrested for burglaries. So this one I put in here just so that you could try using the p-value method instead of the traditional method, since those are our two methods that we use with hypothesis testing. However, I'm not going to do the example. I'm actually going to leave it and suggest that you try it on your own. So I'm going to say, try at home. This one is in the textbook. So I'm not just going to leave you with an example with no answer. So this example is in the textbook with this section. It's one of the ones that they walk through. So I put this in here so you could attempt it on your own and see if you can do it. But then you also have an explanation to look at after. So try this one on your own because, yeah, we've done a lot of traditional versus p-value methods. So I thought, here's a chance for you to try it. So if you get a chance, I recommend trying it out. It's not too bad, and it's in the textbook. Okay, and I put all the steps here still for doing it. So you still have like determine the p-value, all that stuff. Okay, so our last thing in this section is how to do a confidence interval for the difference between two proportions. So we did this for the difference between two means. So naturally, we're going to do it for the difference between two proportions. So let me write down the formula for this. And this is also why I thought making it open book, open notes would just be way better, because there is literally, like, I swear, 2 new formulas for each section. So it just seemed like a lot. But anyways, the formula is P1 hat minus P2 hat plus or minus Z sub alpha over 2 times P1 hat Q1 hat N over N1 plus P2 hat times Q2 hat over N2. Okay, and then we're going to do an example and find the 95% confidence interval for the example that we just did together. So let's see. Let me write down what we had from that example. So we found that P1 hat was equal to 0.35. We also found that Q1 hat was equal to, oh wait, no, we didn't have Q1 hat. I'm sorry. Hold on. We had P2 hat was equal to 0.71. Okay, so we do need to find Q1 hat and Q2 hat. But if you think back to like when we've been doing proportions, Q1 hat or Q bar is always 1 minus whatever that P is. So Q1 hat is just 1 minus P1 hat. Same as how Q bar is just 1 minus P bar. They're like complements of each other. So when you add them together, you should get 1. So Q1 hat is just 1 minus P1 hat. So Q1 hat equals 1 minus P1 hat, which is equal to 1 minus 0.35. which is 0.65. And then doing the same thing, Q2 hat is 1 minus, oops, sorry, 1 minus P2 hat is 1 minus 0.71, which is 0.29. And then just a reminder, we had N1 was equal to 34 and N2 was equal to 24. All right, the last thing that we need is the Z multiplier or Z sub alpha over 2. But these ones are common, and I remember giving you a chart, like, feels like forever ago, like a chapter or two ago, with all the possible Z multipliers on it. So when we have a confidence interval of 95%, we know that Z sub alpha over 2 is equal to 1.96. If you need a refresher on that, I recommend going back and looking at the lecture notes, because we went through deriving how to find these multipliers, and then I just gave you a list of common ones. Okay, let's put everything together. So we have P1 hat, which is 0.35, minus P2 hat, which is 0.71. And then we add to it, and we have our Z multiplier of 1.96 times the square root of 0.35 times 0.65 all over 34. And then 0.71 times 0.29, oops, sorry, over 24. Okay, and then you just have to plug this into your calculator and simplify. So you have to do it when you subtract this thing on the end, and then when you add that thing on the end. So I will let you guys try this on your calculator so that we make sure that everyone's doing it correctly. So go ahead and find the confidence interval for me, and then send me a private chat of those two numbers that you get. Okay, so I did get a few answers, so let's just go ahead and write down the correct one. So if you plug this into your calculator, both adding it and then subtracting that term on the end, you should get that P1 minus P2 is sandwiched between 0.0118 and 0.0602.
When you do the review, can you do it on the screen, like on your calculator, and show us how you're putting it in?
Oh, do that right now. Let me do it. It's a good idea. Okay, let me stop sharing and bring my calculator up. Okay. All right, so first I'm going to do like adding the whole square root term on the right, and then the second time I'll do subtracting it. So I will warn you, I'm not sure if you need as many parentheses as I'm gonna put, but I just don't trust my calculator, so I just put parentheses. So I'll put parentheses and do, actually, let me get my keyboard. 0.35 minus 0.71. Okay, so I have that, and like I said, I'm gonna do the addition one first. So I add to it, and then I have 1.96, and then I'm gonna multiply that. So I'm gonna put parentheses. Like I said, I don't know that you necessarily need them. I'm just over cautious. And then I'm gonna put my square root in there, and let's see. Oh man, this one doesn't have a fraction thing on it. My calculator has a fun little fraction thing. Because I don't think it does. Maybe it does. Not sure. Okay, I'm gonna do parentheses then, and then 0.35, and we're multiplying that by 0.65. And then that is getting divided by 34. Honestly, I think you might need another set of parentheses because you don't have like the fraction thing. So I'm gonna put in another set to be super safe because my calculator has a little fraction thing on it, so I don't have to do that. But let's see if it just lets me put another thing. Okay. It's gonna make me retype the whole thing. All right, give me 1 second. Times, and then divided by 34. Okay, cool. All right, so that is like the first term under the radical there. It's on the top in the numerator 0.35 times 0.65, and then the denominator it's 34. You kind of see that like in terms, I separate things with parentheses. Just because I've had like too many instances where like my calculator doesn't do order of operations correctly or something, or like it doesn't understand what I'm typing in, and so it gives me something wrong. So anyways, then I'm gonna add to it, and I have another fraction, and I have 0.71 times 0.29, and then this is divided by 24. Okay, parentheses to finish it off. And then that should be good. Yeah, there we go. Okay, negative 0.11779, which then I just rounded to be negative 0.118. Let me see if you can do this, but I think you used to be able to just come up here and like use arrow keys to select this. Okay, if you do that, it retypes it out for you, the whole thing, and you can just go back, because like obviously that was kind of a hassle to type. So instead of typing the whole thing over again, literally to just change a minus sign, we can just come back here. It does take a second, but it takes less time than retyping. Oh, okay. And then you can just change the plus to a minus. And then you should be able to hit enter and get the other one. Yeah, which is 0.602. So that is how you can do it on this calculator. Yeah, if your calculator has a nice little fraction button, then that's kind of nicer, but I'm out here using a TI-30, so it's a little less complex. Yeah, any questions on how I entered this in? Yes. Yeah, I have just found that using more parentheses is always better because sometimes your calculator, like, I don't know, it just like, so like if you miss, let's say like the double parentheses here, it literally might take like, it might do 0.35 times 0.65 divided by 34. So it's not like dividing the whole thing by 34, it's only dividing the 0.65 by 34. So if you ever want to make sure your calculator understands, hey, this whole thing is like one term, I'm dividing the whole thing by 34, always just throw on a set of parentheses to be safe. Because yeah, sometimes it doesn't understand what you're trying to tell it. And so it just does what it thinks you're saying and it's not right. So good idea, Michael. Thank you for asking because I have not thought to do this and actually show how to type things in. So I can also do something similar in the review, maybe with other types of problems. So okay, let me go back to my notes. Okay. Now we got the notes back up. That was the last thing in section 9.4, was just finding this confidence interval here. So we are going to move on and sort of say goodbye to hypothesis testing. Not quite, but almost. You're still going to use it in the next section, but the next section talks about more than just hypothesis. So I'll save this and then start 10.1. Any questions though before I move on to 10.1? Okay, so 10.1, we have done part of this section. We did the scatter plot portion. So 10.1 talks about scatter plots and correlation, and all we talked about at the beginning was just scatter plots. So there's a little recall in here because that was a long time ago. I think that may have been week 1. So that was a really long time ago. So there's some definitions in here in case you forgot. So the first thing that says, many times we're interested in determining if there's a relationship between two variables. So if there's maybe like a relationship like, oh, if this variable increases, does the other one increase as well? Or if this one increases, does the other one decrease? Just seeing if there's any relation between two variables. And that's where scatter plots and correlation come into play. So a scatter plot is going to be a graph of ordered pairs of data values that's used to determine if a relationship exists. So I think I had you do a scatter plot on like exam 1, and I gave you a bunch of points that were like X values and a bunch of points that were Y values, and you just plotted the pairs. And when you plot the pairs of data points, you can kind of tell if any form of a relationship exists. Then we get into two types of relationships. One of them is a positive linear relationship. So a positive linear relationship exists when the points fall approximately in an ascending straight line. So what that means is that as the X values increase, the Y values also increase. So it's a straight line that has a positive slope. So as one increases, the other increases as well. Okay, but with that, we could also have a negative linear relationship. Let me actually draw just a little example. So a positive linear one would be like that. And then a negative one exists when they fall in a descending straight line. So that would be where like one increases and the other decreases. So like as X values are increasing, the Y values are decreasing. Okay. So then if we want to know about a relationship, you probably want to know what the strength of the relationship is. Like if you find that these two things are related, but they're like barely like related, do we really consider it like to be a linear relationship? Like, where do we draw the line? So this is where we get into actually being able to numerically describe a relationship between two things. And this is what's called the correlation coefficient. So you might remember when we talked about scatter plots, we talked about linear regression and scatter plots, and I said, oh, there's this thing called the correlation coefficient, but I'm not covering it in this section. Well, here it is, and it's here, and now we're covering it. So like 6 weeks later, we're going to talk about it. And the reason that we're waiting until now is because we talk about the correlation coefficient with hypothesis testing just a little bit. So you kind of have to have that knowledge to discuss it. Okay. So when data points follow roughly, oh, okay. All right. When data points follow roughly a straight line trend, the variables are said to have an approximately linear relationship, which makes sense. If you look at a scatter plot and the points kind of look like they fall in a line, okay, it makes sense. We might call that linear relationship. And it says if we have a linear relationship, we can use the correlation coefficient to help determine the strength of the association. All right, so what is this correlation coefficient? It is computed using some sample data. It measures the strength and direction of a linear relationship between two variables. The symbol for the sample correlation coefficient is R. And then the symbol for the population correlation coefficient is this thing that looks like a P, but it's called rho. So if you're doing the correlation coefficient for your sample, we talk about it in terms like as R. That's what we refer to it as. But if it's for a population, it's denoted by this symbol here that really just looks like a fancy P. It is rho. I think all the examples we're going to do are really with samples. So you probably don't need to know too much about the population correlation coefficient because everything I'm going to touch on is R. Like I said. Okay. So what is this correlation coefficient though? Like what does it look like numerically? It can take on values between -1 and +1. So if you have a positive value for R, it means something different than if you have a negative value for R. So I'm going to write down what each of those means. So a positive value for R is going to indicate a positive linear relationship. Makes sense, positive, positive. And likewise, if you have a negative value for R, it indicates a negative linear relationship. So any value that's close to +1 or -1 is going to indicate a strong linear relationship. And I think there's there's some examples in here that talk about it, but if you have a positive value and it indicates a positive linear relationship, the closer to 1 that you are, the more strong that relationship is. If you have a negative value for R, the closer you are to -1 indicates a stronger linear relationship. So this indicates a strong linear relationship. So let's say you have like an R of like -0.98. You would say, okay, that's a strong negative linear relationship. If you have an R value of like positive 0.98, then you would say, okay, that's a really strong positive linear relationship. So it makes sense that maybe something in the middle of those means there's really no linear relationship. Because the closer we are to +1 and -1 means the stronger the relationship is. So if we fall just smack in the middle, near 0 indicates there's no linear relationship. So if you wanted to draw like a little number line, you had like 0 here in the middle and then 1 here and -1 here. You could say this would be no linear relationship. Close to 1 would be a strong positive linear relationship. And then close to -1 would be a strong negative linear relationship. So your R value is going to fall anywhere between -1 and +1. And based on what it is, you can kind of infer maybe, is this a strong or is this like a really weak relationship? Like, is it positive, but it's barely positive? And that's probably going to be like a weak positive relationship. Okay, so that's what the values of R mean. So then I have this figure from the textbook here that just shows you some examples of like linear relationships and then what the R value is. So let's look at A. A says R is 0.5. Okay, well, these points here on our scatter plot, they do have a somewhat like positive, like they are, it has a, trying to say, the points, like as one increases, the other increases. So you can see that it has a positive relationship here. So they both increase together. And the points are like in a line, but like, I mean, like they're in kind of a line shape, but they're not like really aligned. Like it's kind of a blob that's moving in an upward direction. Okay, so an R value of 0.5 kind of makes sense. They look like they have a relationship, but I don't know, it's kind of in the middle. It's not really strong and it's not really weak. And then we have an example of where R is 0.9. So these are definitely positive because as one increases, the other does. And these are more in a line. So it's the blob is a little thinner here, and they definitely resemble more of a line. Then we get to a perfect R of 1, and they are just a line, basically. Then you see the opposite here. So like this is negative 0.5, where it's a negative relationship because as one increases, the other decreases. But it's similar to example A, where like they're not super strong, not super weak. Then we have E, which is negative 0.9, definitely a negative relationship because as X increases, Y decreases. More resembling the line here, not a perfect line, but it's a pretty good relationship, pretty strong. And then we have the perfect where R is -1 and they are just in a line that's decent. All right, any questions on these? All right, so now we have to talk about how do we calculate what R is. So like that's great, R is this value, but how do we calculate it? I'm gonna write this formula, and then I'm gonna tell you that it's way too ugly to do by hand and that we're never gonna do it by hand. So I'm just gonna write it. You're not gonna need to use it, but here we are. So R is equal to, get ready for it, n times the sum of xy. And yes, I have personally had to do this by hand before for a class, which is why I'm never going to make you do it by hand. Xy minus x, the sum of x times the sum of y, all over. Okay, my notes slightly got cut off. Let me make sure that this, I mean, you're not going to need to use it, but let me just make sure this is correct. See, that goes to show you how much like I don't use it because I don't even have it memorized. Okay, this is a different formula. Hold on. Okay, no, I think I got it. Okay, yeah, we're good. All right, so on the bottom now, it's even uglier, if you can believe it. So we have a square root, and we have n times the sum of x squared minus the sum of x squared, oops, missing a parenthesis, there we go, times n times the sum of y squared minus the sum of y squared. Like literally the ugliest thing. Imagine if you had 10 data points and I asked you to do this by hand. Yeah, I will never. So just a mental note, too ugly to do by hand. And definitely, like, if you're going to continue doing stats classes and you learn like programming with stats, if you use anything like R, there's literally just a thing in R where you like input your data and put like it's some like function and it just spits out what R is for you. So you will never do this by hand. I would never ask you to. Okay. And then we have that we're going to round R to 3 decimal places. So that's just like the standard rounding. And then like it says, you're never going to be asked to do this by hand. So we can look at how the graphing calculator will calculate R. And you actually already know how to do this. So we did this. Yeah, that's fine. You can use Excel. Yeah, I will always just use the calculator because that's kind of like standard for what we show in this class. But you can definitely use Excel to do it instead because Excel has formulas for that stuff too. So that's fine. And I think actually like in the textbook, I think they usually do tutorials in the calculator and Excel if I'm so you do know how to do this already, and that's because when we did linear regression, I showed you how to do it in a calculator, and it's the same process. Because if you think back to when we first did this, we did linear regression, and I said, hey, it's going to tell you this thing called R, but you don't need to know what that is yet, so just disregard it. Now you need to know what it is. So it's the same process as when we found the regression line. Now you just are looking at what R actually is. So let's do an example of how to do this. And then I think we'll stop after doing the example in the calculator. So let me pull my calculator up and we're going to do an example. So we're finding the correlation coefficient between the height and hand span data. So if you really throw it back to when I think I first talked about like linear regression and scatter plots, we used this data right here between height and your hand span. Well, now we're going to find the correlation coefficient for it. So let me pull up the calculator. Okay. All right, so there's some instructions in here. So you do have to turn this thing on. You have to go to like this menu and hit diagnostic on, but I've already done it and you only really have to do it once, so you should be fine. But if you get a wrong answer, maybe try doing that. And it's in the notes, but I'm just gonna skip that step. So first thing we're gonna do is type in our X data points in our little L1 variable thing. So all you do is hit the stat button and then you hit enter. And then you're given L1, L2, L3, whatever, these like categories. So we're gonna type in all of our X values for L1. I've already done that because I did this example before class. So I typed in, 71, 69, all the way down to 65. And that is all the heights that we have. And then I typed in the hand span in for L2. And that is just known as kind of like my Y's. So I have my X's here and my Y's here. So I've typed them all in. Let me just double check that they're all correct. Yep. Okay, cool. So those are all in there now. So once you get those in your calculator, all you have to do is hit the stat button one more time. And then you come over to the calculator part right here. And then you just press 4, which is the linear regression thing. So like I said, you find the R value when you do the regression, and it just gives you that like statistic. So if you hit 4, make sure that your X list is L1 and your Y list is L2, and then you're just going to hit enter. All right, and it's going to give you a few things. So it's going to give you the regression line, which we did a while back, but it's also going to give you R and then R squared. So yeah, it gives you both of those values. Sometimes you use R squared for things, but I don't know, it's kind of funny because like it's not that hard to just like square it in your head, but I don't know, they give it to you. So here's R and R squared, so it's not too bad to do with the calculator. So our R value is 0.753. So let me go back to my notes. This is 0.753, and I rounded it to 3 decimal places. So based on that, if you had to make a guess, would you say it has a strong positive relationship or strong negative relationship? You can send a chat. I don't. Good, yeah, strong positive relationship. It's positive and it's, I mean, it's not like really close to 1, but it's closer to 1 than it is to 0. So, yeah, so good. But then we get into like this whole like concept of like, okay, well, where is the cutoff for like a strong positive relationship? Like, where do you draw the line and say this one's strong, this one's not? Kind of like relative. Like, what do you think? And that's kind of like when we would just look at a scatter plot and say, oh, does this look like it has a strong relationship? I mean, I don't know. Like, it's better when you have a numeric thing to kind of like quantify that relationship. So it says, at what point is R high enough to conclude that there is a significant linear relationship between the two variables? Or is the value of R by chance? So did I just randomly get samples of data that happen to be like correlated, but that wouldn't happen all the time? So surprise, surprise, to do this, we're going to conduct a hypothesis test. So we'll be doing a hypothesis to see if there is a significant linear relationship or if we can't conclude that. But I am going to leave that for next class period. So we will do the actual hypothesis testing on Thursday. That's how we'll start class off, and then we'll try and finish 11.1 as well. But are there any questions on this content? Okay. I'm going to stop sharing, and since I am ending like